organic matter quality, oxygen index and hydrogen index. We make a relation between hydrogen index and oxygen index, modified Frank-Rivlin diagram. In Chatian, showing that we have mixed source rock type 2 and type 3. And in Rupelian age, we have a type 3 source rock gas prone. And this is map for oxygen index and hydrogen index along the area. The red flag type 3 gas prone, and the orange flag is type 3 and type 2 mixed, and the green color is oil prone. Hydrocarbon type index S2 over S3 also show most of samples in Chatian and Rupelian type 3 gas prone. Production index, most of sample showing that all samples or most of samples in oil generation window. Tmax, the relation between hydrogen index and Tmax, showing most of samples located in the mature stage in Chatian and Rupelian age. And this is map showing the Tmax along the area. The blue is immature, green onset of oil generation, and the yellow color onset of oil expulsion. Vitrinite reflectance. Vitrinite reflectance in Chatian, most of samples in oil window. And in Rupelian, the sample, some of wells go to the onset of gas generation and wet gas. And this is map for vitrinite reflectance along the area in Chatian and Rupelian, showing that the immature area in blue color, oil window in green color, and the gas window in red color. Now build hydrocarbon generation model. To build hydrocarbon generation model, we should firstly know the present thermal and geothermal history. The surface temperature ranging from 14 to 22 degrees Celsius, and the bottom hole, corrected bottom hole temperature ranging from 70 at the east, and then go to temperature about 200 degrees Celsius at the basin in the central area, and generate or create a model geothermal gradient and for the area, and the averaging geothermal gradient in the area is about 27.5 degrees Celsius. And this is a 1D basin model for one of drilled wells in the basin model, in the basinal area, showing the oil window start at Tortonian age, the gas window start at Chatian age, and this is two charts for the amount of hydrocarbon, gas and oil generation in Chatian, and the gas and oil generation in expulsion in Chatian also. Now, we try to predict the hydrocarbon potentiality in the area and estimate the amount of hydrocarbon in this area. We use the thickness map for Chatian and Rupelian, and put on it the maturity of the area from vitrinite reflectance, and delineate the polygons of gas kitchen and oil kitchen in Chatian and Rupelian, and calculate the area by kilometer square, and put it in this equation incorporated by Mushir and Walbus, and calculate the estimate hydrocarbon generation in offshore area in Chatian and Rupelian. The total generated gas are about 778 TCF. We discovered only about 7 TCF in the area. So the undiscovered remaining reserve is about 775 TCF in the offshore Eastern Nile Delta. Now go to the summary and conclusion. Summary and conclusion. The structure surface map of top Oligocene are ranging from 1,450 meter at the southeastern part to more than 6,750 meter in the west part of the area of interest. Net to gross map for Oligocene bars show the extension of fluvial channel from the onshore Nile Delta toward the north offshore area. Oligocene sandstone reservoir have net reservoir from 20 meter to 70 meter, have net bay from 2 meter to 35 meter, of net to gross about 50%, of porosity ranging from 8 to 25%. The average water saturation ranging from 32 to 59. Salinity of Oligocene in the area ranging from 5,900 ppm to 26,000 ppm, mainly brackish water, and the RW used in petrophysical evaluation from 0.05 to 0.27. The TUC value in Tina formation Oligocene age ranging from 0.28 to 3.28%, which indicate is poor to good potential. The quality of organic matter showing that we have gas prone type 3 and mixed type 2 and type 3. Farewell mostly is we have our farewell formation belong to Kherjon type 3 gas prone. Most of Tina formation is a thermally mature and started of onset of oil generation and oil expulsion. The burial history we conduct, we use just geothermal gradient about 27.5, heat flow from 41 to 48, 49, vitrinite reflectance from 0.37 to 1.09%, of hydrogen index ranging from 11.5 to 357. Organofishes 45% DE, 50% F, and 5% 4P. Finally, the total accumulated reserve is about 782 TCF, and now the demand of reserve is about 775. Thank you for your attention.
Thank you. Thank you, Mr. Mahmoud, for this presentation. And before to go to the question, I have to precise that Mr. Mahmoud is currently working with EGAS based in Cairo as exploration manager.
Yes.
Okay. Now, please, if you have any question to Mr. Mahmoud about his speech. Yes.
Hello, my name is Jan-Pieter van Dijk from Dragon Oil. Did you do this study in the framework of the bid round, which is going on?
Yes, Betrel, yes.
Yeah?
Yes.
Okay. So it should be a little bit more confidential, maybe. Anyway, so my question is, of course, we are looking at these big numbers, but let's be fair, it looks it's more in only Oligocene sands than has ever been produced in the whole of Egypt, right? On gas. So let's say it is not something like this has been generated and only 7 has been in place. So how much is actually, from what, if you know this, I have no clue, how much is actually produced from the Oligocene?
From Oligocene?
From these sands, Oligocene.
From Oligocene, we start already the first well put on the production named Atoll Well, BB company, and the reserve of this well about 1.5 TCF, and is produced daily about 0.5 BCF per day.
Okay. Of course, a wellhead doesn't have a reserve like a TCF. It's a field.
For field.
It's a TCF.
Field.
600 BCF maybe.
Yes.
Not a well.
Nowadays, from 3 wells. Nowadays, drilled 3 wells to develop this field, and this is the first field testing Oligocene and produced from Oligocene at deeper depths in Chatian. And also we have many discovery for Oligocene, but there is no development in it due to, the high temperature, high pressure regime. So nowadays there is a technology to start producing, and already start producing at this level of depth.
Okay, so you have one well which is actually flowing.
From one well?
From one well.
Yes, 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 yeah. And then drill.
But you didn't really. I didn't really actually understand how many million scuffs per day. The flow rate.
I don't.
I understand you have sort of an expectation of the reserves that this well could add, but what is the flow rate? If you know,
I don't remember daily.
It's not important.
Yeah.
Anyway, let's be a little bit more realistic on the numbers, I would say, because a TCF is already very nice. Field,
but the area is likely this age is in Egypt is a virgin. There is no more wells drilled in the area, and this sediment of this age proved as is the main source rock for Miocene and the Pliocene discoveries.
That's my second question, actually. Sorry that I take the lead of these questions to the public. My second question is actually, you have a lot of gas produced from this source rock. Okay, very good.
Yeah.
We believe, no problem. It's nice. You did your best practice homework. Good.
Yeah.
But now, where is this gas? Of course, it's not in the Oligocene sands, I suppose. You are already giving the answer basically to my question.
Yeah.
So even if it is a few hundreds of TCF, who knows where it is gone? Is this correct as a conclusion? It can be in the Pliocene, can be in Miocene. And so a lot of this gas is already produced in the Miocene and Pliocene fields.
Yes.
Okay?
Yes.
Good. So whatever you calculate as reserves is not something we can say still to be found, because we must calculate all the Pleistocene and Miocene fields, how much TCFs they have already in place.
Yeah.
Let's say, even not produced, doesn't matter, in place. And then we make a realistic estimate of how much this source rock maybe has also given to the Oligocene.
Yeah.
Is this correct?
Yes.
You agree with this? Okay.
Yes.
Good. So which is a little bit more complicated, of course. We
Yes.
don't have the answer, but okay. So that was actually my question. You answered already. Good.
Okay, thank you.
So what is your plan? Which is our interest now. What are you doing? You are proposing to drill more wells in your Oligocene.
Yes, but you know that the Oligocene wells need big companies, have a very big budget. So nowadays we promote to big companies like ExxonMobil, Noble Energy, and we have nowadays a bid round, a license bid round, and this all of these big companies worldwide coming to Egypt, and we hope these companies work
partnership in your adventure.
Yes, yes.
So how much is the cost of a well?
The cost of well, the first Oligocene well costed about $120 million.
Yeah, that's quite
the second
expensive.
well this is for Atoll, for example. The second well costed $40 million.
Yeah.
So the first one, due to its wild cat and use many precautions due to high pressure, high temperature. After the discovery, the company learn and know that anything about the area, and then the second well costed only $40 million.
Yeah. You had some discount from the
Yeah, yeah.
Still expensive wells, of course, offshore.
Yes.
How much is the water depth?
But the profit is very high, because the lowest reserve in Oligocene wells, 1.5 TCF.
Yeah,
We have three
I
big
understand,
discoveries.
but you're not telling me the flow rate.
Yes.
So I don't know how much it is, how good it is.
Yes, there is a well drilled by BG now Shell,
Yeah.
named Notice, also found reserve about 2 TCF.
Yeah.
And another well called Salamat, also by BP, more than 2 TCF. So the profit from this well is very high comparing with the cost.
But again, it is not the volume you addressed. You have to have the flow rates to know the profit.
Yeah.
But anyway, thank you very much. Very interesting.
Welcome.
Thank you. Any question? We still have time for 2 or 3 questions, huh? Please. Okay. I have a question for you.
Okay.
Now, in one of the slides, you show us that there is some degradation of the reservoir quality in depth.
Yeah.
Above 3,000 meters, there is a dramatic deterioration of reservoir quality.
Yeah.
Is this reduction of the porosity and permeability is related to the overburden, to the burial, or to some diagenetic alteration?
Of course, due to the high pressure, the overburden pressure, due to the big thickness of shale, make a pressure on and decreasing the porosity. Due to that, we make a relation between the porosity with depth. We found that the overburden lithology, it's the main factor affected the decreasing in porosity, because we drill till 7,200 meter. We found also the porosity decreasing with depth, and from thin section we found no facies change. It's deltaic facies. But the compaction is due to the high pressure.
But it was well documented by logs, high density, and I guess related to some parts of the ground.
Yes, of course.
And in such case, you produce from this poor reservoir quality unstimulated or stimulated?
We only start to produce from porosity about 16, but until now we didn't put like a development release, but didn't start yet by Shell company in porosity about 8%. But until now we didn't produce. It's planned to produce from this low porosity.
For gas is okay, but for oil?
No oil in this.
No oil.
No oil. If gas. Gas prone, no oil. The oil only in the shallow section, nearest the eastern part of Nile Delta. But mainly in the central part is gas prone.
Okay. Now I have a question regarding the vitrinite reflectance of the Shatien and also the Riparian source rock.
Yeah.
In one of the slides, most of the area located to the east and to the southeast, the vitrinite reflectance is less than 6% and 0.6%, and the source rock is immature.
Yeah.
And this is related to some cooling, related to some uplifts or some unconformity or some.
Is related to the uplift, as you said, related to the uplift of the Cretaceous. You know, at the upper Cretaceous, we have a big compressional regime, make the eastern part is become higher than the central part of Nile Delta basin. So it's related to the uplift of compressional regime of the Cretaceous. And also the Oligocene is coming over Cretaceous, so the Oligocene affected by this uplift happening in Cretaceous.
Okay. Now about the trapping mechanism.
Yeah.
And the hanging wall close to this Timsah fault,
Yes.
major fault. There is no indication of some turbidite or some feature, a sliding feature
No, in this
from
area,
the high to the basin, I mean.
the turbidite, we found it in the deeper, in the ultra deeper area near the border of Egypt with Cyprus. But in this area, mostly of fascias is deltaic fascias. Deltaic fascias,
Yes.
fluvio-marine fascias. Rivers come to this area and load the sediment in the area. That's it.
The last question.
No,
is
no, no problem.
If there is any analogy
Yeah.
between the oligomycin here and the gas discovered in the recent, by ENI recently, and the Zohr structure, and if there is some build-ups in such oligocene reservoir,
You
at
know,
least in the paleohighs.
I present, if we go back to the presentation. Hi.
Go back, please, to the presentation. Yeah.
This line is passing from southeast to northwest. You see, this is a paleo high. In green color is a Cretaceous.
Yes.
Zohr is a north. Zohr we tested is a Riffel carbonate, but the story in Zohr in the Cretaceous when the new thesis is opened happened volcanic eruption make this area of Zohr is become high and becomes a turbidite and becomes a Riffel built in over this basement. In this area nowadays we try to test the first up structure, this dome, first one.
Yeah.
Drilled now. So we have a doubt if these high structures, this and this, is due to compression regime happen in Cretaceous, or this is another analog to Zohr, because in past we didn't believe that in this area we haven't Riffel carbonate.
Okay.
So after finish this well, drilled at this location, we can say that if this is due to this high structure, due to the compression regime happen in Cretaceous, or due to the uplift of what's called magmatic eruption, make this area is high and formed Riffel carbonate, like Zohr.
Even in shortening context, there is like this paleostructure. We have a big chance to find some build-ups at the top or at the crest of the structure.
Yes, but the lithology, the facies is a big problem for us because most of wells drilled in this area is tight carbonate,
Okay.
is deep marine pelagic carbonate. But Zohr is a Riffel carbonate, so the environment in this area mainly pelagic, deep marine pelagic. So we will test it, inshallah. If it's, we hope become big discovery like Zohr. After that, if this well is a Riffel, it will change also the area because we have another one and higher than so.
Okay.
We hope to become.
But at least there is one similarity about the seal. The missing
Yes. In Zohr we have about 2,000 meter of salt,
Oh, yes.
so we have a good seal. But in this area, one of the risk in this area is thickness of salt here, as you seen is very narrow in thickness, and most of sediment is a shale sediment. Within it, sandstone. So the seal, one of big risks in this area.
If there is no question, thank you very much, Mr. Mahmoud, for this nice presentation.
Thank you.
And now we move to the next presentation of Ms. Noura, Noura? Najwa, or Ms. Najwa? Voilà. About fascists, and the talk is dedicated for fascists and high resolution sequence stratigraphy of the Tortonian incised valley, Sawa formation in northeastern Tunisia.
Thank you very much. Today I will start by the presentation of the phases and high-resolution sequence stratigraphy of the Tortonian incised valleys discovered in the Sawa formation in northeastern Tunisia. So I will start by the definition of the incised valley. What's the meaning of this incised valley system? The incised valley system are scientifically and economically important depositional settings. They are erosionally topographic structures, typically larger than a single channel, and the base of the valley constitutes a regionally erosion surface across which there is an abrupt seaward shift in depositional phases. The erosion surface may be mantled by a pebble lag. Here in the picture, we see an actual incised valley seed in Alberta, Canada. Incised valley are also an important structures in sequence stratigraphy. In fact, incised valley are formed during periods of low accommodation, and type 1 inconformities and sequence boundary are generally marked by the presence of the incised valleys that were eroded by fluvial action during the relative sea level fall. The recognition of the incised valley system can mark and identify a sequence boundary type 1. This system have an economic importance. In fact, the petroleum geologists have focused on incised valley system and estuarine deposits because of the economic significant quantities of hydrocarbons produced from reservoirs hosted by the field on incised valleys. Different authors estimated that 25% of worldwide off-structure conventional petroleum traps in clastic reservoirs are hosted within incised valley system. So in this table, we can see that there is many examples of tidal phases in petroleum reservoir, and different incised valley system and tide-dominated delta and tide-influenced delta and incised valley field system are discovered mainly in and produced hydrocarbon from Nile Delta Egypt, Niger Delta, and Sumatra Basin, Indonesia. This series and incised valley are discovered mainly in the Miocene series. Whereas in the Gulf of Hammamet, Miocene series produce hydrocarbons, and the accumulation of these reservoirs are discovered mainly in the Ain Ghab limestones, Birsa, and Sawef sandstones. The Cadmont outcrop can play an important role in improving understanding of subsurface reservoir architectures and provide important information on geobody size, geometry, and potential connectivity. So several work have been made and in the outcrop of Cadmont Peninsula. And we can see here the Ain Ghrab limestone that correspond to the equivalent reservoir in the Gulf of Hammamet. Here we see the limestone of the Ain Ghrab formation that correspond to a transgressive limestone that overlies the Fortuna group. This mudstone to packstone limestone present mainly a bryozoan marine and corals and pectinids. This fauna can increase dramatically the reservoir quantities. In the Birsa reservoir equivalent that correspond to the Biglia formation in the Ain Ghrab, in the Gabon outcrop analog, we can see, first of all, at the lower part of this formation, a parallel lamination, a herringbone structure, and we have here a stacked sets of dunes. This medium and coarse-grained sandstone correspond to foreshore and tidal flood deposits. In the middle part of the Biglia formation that correspond to the equivalent of Birsa formation, we can see here a very coarse-grained sandstone with quartz pebble that correspond to foreshore faces. We see here a medium to grained sandstone filled and with high degrees of burrows, essentially the scolitous burrows. These high degrees of scolitous can increase the quality of the porosity and the quality of reservoir. In the upper part of the Birsa formation or Biglia formation, we see very coarse-grained sandstone with mainly ostrea. This also can increase the quality of the reservoir. For the Saweh formation in the Jebel Abdurrahman area, we see here essentially a prograding sequence, and the Saweh formation begins by thick offshore mudstones overlain by a succession of mudstone to sandstone prograding parasequences. In the middle of it are encountered lignite beds. The upper part of the formation is again made of a large number of parasequences resembling those of the lower part. So the target and the focus of this study is the Gabon Peninsula that is located in the northeastern end of the African foreland basin and in the north of the Pelagian block. For this work and for this presentation, I will present only the Miocene series in the Jebel Belabia area near the Hawaria village, when we see that the faces succession is completely different from the Jebel Abdurrahman area. So the detailed sedimentology and high-resolution sequence stratigraphy have been used to show the architecture and the complexity of the depositional and environment. For that, several and detailed stratigraphic sections have been made in this monoclinal. For this presentation, I will focus only on two stratigraphic sections, section 1 and section 2. For the section 1, first of all, we can see the Ain Ghrab formation that rests directly on the Fortuna group. This formation corresponds to transgressive limestones and contain abundant and diversified marine macrofauna and composed mainly of pectinids and echinids. And we see here that the Ain Ghrab formation is exactly the same faces in what we see in the Jebel Abdurrahman area. So after the Ain Ghrab formation, we have the Mahmoud formation. This formation overlays the Ain Ghrab formation, and it consists of a series of gray maars with a glycolitic horizon at the base. And this formation contains planktonic foraminifera and represent open marine sediments. And in the same way, it's exactly the same faces like the Jbal Abdurrahman area. When we see the difference in the Biglia formation, where conformably above the Mahmoud formation sits thick units of gray and black mudstones that grades upward into heterolitic succession here of alternating gray mudstone and fine-grained sandstone beds with sharp and erosive beds. The sandstone beds correspond to storm beds. Some sandstone beds can contain plane parallel to low angle lamination and wave repellent top. This interval is interpreted to be deposited in an offshore and offshore transition environments. And here we see the difference between the Jbal Abdurrahman area and the near the Hawariya village and the Jbal Abyad area. The upper parts of this interval is incised by large valley systems. The base of these valleys constitutes a regionally erosion surface and is interpreted as a sequence boundary. This erosion surface is locally overlain by mainly mudclats and wave-repelled structures. This erosion surface marks an abrupt and sharp-based basinward shift of faces, and it can be traced throughout all the staging area. Now I pass to the section 2. And in section 2, I will focus only on the Sawef formation. The Sawef formation here present and record several episodes of erosion and filling. And the stratigraphic architecture and the sequence stratigraphy analysis of this series shows that we have a stacked system of transgressive system tract and high stand system tract. I will start by the presentation of the transgressive system tract. The transgressive system tract is composed of a high number of fining upward parasequences and is made mainly by fine to medium sandstones with planar cross stratification, herringbone structures, current triple, and mud traps. Laterally, we can see also different sedimentary structures like flazer and wavy bedding and wave ripple. So we can conclude that based on their lenticular geometries, the erosive relation with the underlying offshore transition deposits, and the fining upward trend, these phases are interpreted as tidal channel and tidal bar deposits. This can indicate the deposition in tide-dominated and estuarine environments. The high stand system tract is composed of a high number of thickening and shallowing upward parasequences. These parasequences record progradation and comprise at the base lower offshore deposits that pass gradually into offshore transit deposits and shore face deposits. The wave influence is demonstrated here by the occurrence of hummocky cross stratification. Here, you can see here. And the wave ripple. And the presence of the storm beds. So in conclusion, we can say that the Sawef formation provides an excellent example of incised valleys filled by tidal estuarine systems. Sequence boundaries are identified at the base of different incised valleys that erosively overlay marine offshore transition deposits. Inside the valley are filled by tidal channels and tidal bars, deposits during a relative rise of sea level, and form the transgressive system tract. This system consists of a series of stacked fining upward succession and tide-dominated estuary. The high-stand system tract consists of stacked coarsening upward and shallowing upward succession of wave-dominated delta system. So, the reservoir prediction. Recognition of these channelized sandstones that correspond to the field of incised valleys has an important implication for reservoir prediction. These sandstone deposits can form an excellent potential reservoir traps for hydrocarbons in the Gulf of Hammamet. And thank you for your attention. And if you want to have more information about the Tertullian series in the northern Tunisia, in front of the Nebs, we have published recently an article where we discovered a new deltaic environment in Tertullian series. Thank you.
Thank you very much. Thank you very much. Any question? Yeah. I have one remarks. When I saw this presentation, there is really a great input from the student, from the research, to better de-risk your hot prospect in the Gulf of Hammamet. And in addition to that, Mrs. Najwa precised that there is, Narjis, there is possibility of development of incised Paleo Valley and the Oligomyocene. And this really, it's very, very interesting feature, because in addition to the structural trapping mechanism in the Gulf of Hammamet, there is possibility of stratigraphic upside associated to this deltaic sandstone associated to Baraka Sawaf formation.
Yes.
And I was surprised by the presence of the scolitos in the Miocene.
Yes, there is scolitos, thalassinoides, and ophiomorpha. Huh? There is different burrows. There is scolitos, ophiomorpha, and thalassinoides also in the Sawaf formation.
What's the difference between the scolitos and the Ordovician scolitos?
Ordovician scolitos are coastal marine. They're practically the same.
Practically the same. Okay. Okay. As Muhammad is present here, I have a question. How much the depth of this incised Paleo Valley and the Miocene?
The depth or the thickness?
The depth of the incised.
Depth is 30 meters. 10 to 30 meters.
10 to 30, and
yes,
the lateral extension?
But it's more than 100 meters.
More than 100
Yes, and we have connectivity between the channel body. For that, it's very good reservoir traps.
Donc we expect a good connectivity between
yes.
this.
We see here in the first. The first slide. Yes, here. The photo is not very...
Exactly.
Here we see the different incised valley, the first and the second, and we see here that it's very well connected.
No, because exactly. It's very important. This type of sand flowed up to 6,000 barrels a day from Baraka 1 well. A huge rate.
Different, the incised valley produced mainly in Texas and in many regions in the world. I present only the Miocene series, but we start to research in Gulf of Hammamet if you will be.
Okay. Any question? Yes.
Yeah, I feel obliged, obviously. Now, I just came in. My colleague, Hassan Guni, he gave the presentation this morning about our ideas on the prospectivity of some of these Miocene sandstones. I don't know if you... So actually, of course, I cannot be other than uttermost happy on this type of studies, because it helps us to understand the geometry of these sandstones. And
thank you very much.
And my next talk, if we still have some time, I will. But I won't go more in detail than Hassan already did. I will just highlight some other things. But so not so much on the sedimentary environment. We are very curious, of course, to know more about this, because we also believe in the high prospectivity of these sandstones for other reasons. Although it seems to be a mature play, not many people are looking for more than has already been produced. So we all know this, so we should look for different things in a different way. And so we can think of stratigraphic traps, valleys, and the things we proposed on the inverted structures. Now, a little bit my question, looking from your information, I would like to see then, at that stage, a little bit more about the correlations between your sections. Yes. Because you show your sections, very nice, okay, best practice.
I've made
this picture is actually the only one where we see something more, what is happening actually laterally
with these levels. Yes, I've made the correlation, but I don't present here.
Yeah, no, I'm fully confident that you have them. Yes. But I would have loved to see them, because what we must understand, of course, is what is actually the lateral extension of these thickness variations. Is it very gradual, or we can see something on this panoramic picture, but of course it's not
very clear.
It's not calibrated. It's just a panorama with all the effects of the view. So that is one. It looks as if they are not very steep and narrow. They are very wide. Is that correct?
I don't understand the question.
They are wide. They seem to be wide.
Yes.
Not so steep.
More than 100 of meters.
Yes. Now they are very wide, and of course we have these things that are like 10, 20, 30 meters. So what we must understand, if we want to project this on prospectivity offshore, we have to look at seismic inversion.
The seismic profile, we must
try,
see here the
try to see something in seismics which is actually very small.
But we can see here different articles are published for discovering of the incised valley in the offshore and by seismic profile.
Yeah, yes.
We can see here in the seismic profile.
Okay, so again, maybe somebody next time shows some nice time slices or whatever where we can see them. Because in the 3D seismic, from what we have seen up to now, we were not yet capable of seeing things of this size. But we need probably some specific reprocessing and inversion, AVO studies or inversion, at least this one, on the seismic to see something like this coming out. It will be a challenge to detect them, But it's interesting to see. What I see, there is a lot of shale, okay, in this. This is what struck me last year. We did a field trip with ETAP, and we saw some more to the south. It struck me that there is a lot of shale, and of course this makes us worry a little bit about connectivity between these sand bodies and the charge of hydrocarbons.
Yes.
It's easy to charge them on the lower part, and we talk about this maybe in the next talk. Okay. So, well, that's it. My compliments. I hope to see more of this.
Thank you very much.
And it brings me back to 25 years ago when I looked at the Miocene in my studies. So it's a déjà vu. Please.
Just a small additional comment before seismic. Perhaps she has to try with E-logs. With E-logs, I mean the characterization of the sandstone body can be done using only gamma ray and sonic, and we can see how the internal architecture of this sedimentary sandstone body already crossed by the well. So just to compare the scale thickness and the width of the sandstone body, something that has not been yet done, and we have to encourage nurses to do that in the futures. Yeah.
Yes?
Give it.
Where does the sand come from? Actually, you showed some in the last picture of irrigation.
I don't.
Where does the sand come from?
The source of the
I saw
Where
something
the
in your last
source.
picture, all of a sudden regional, but can you highlight?
We have here an. Where we can tell. We discovered here a high, a paleo high in the Gulf of Tunis, here between the Gabon and the Four Deep Basin. We discovered here a paleo high in the Miocene. Yes. And that it
Sorry.
can be the source, and we have also the Saharian source. All the sandstone can be.
Let's think of the petrography.
Yeah.
It is quartzites or
And all the measured of the
Yeah,
currents in the ripple and the asymmetric ripple, etc.
so what are we thinking of reworking from Oligocene or Fortuna? This kind of
Yes,
things?
I work all for the middle and the late Miocene. Since
So it is reworked from because we are in the foreland. We are not yet on the thrusts, right?
Mm.
Yeah. So we need to rework something in the north.
yes, we
Right?
have, yes.
Yeah. Okay. Thank you.
Just I have one comment. In order to better define the geometry of such sand bodies, if we have also 3D seismic, we need to extract some attribute using the OpenDetect. OpenDetect is one of the most useful software to provide you with a better image of this stratigraphic feature.
And we can see also the incised valley with the gamma ray angiography. Yeah. And maybe we can see here in the correlation of the gamma ray and the response of the sandstones.
Good. Thank you very much. Thank you for the nice presentation. And now we move to the next presentation of Mr. Stefano Santoni from Dragon, based in United Arab Emirates. Okay, just few words about the background and the experience of Mr. Stefano. Okay. As former exploration manager of Dragon Oil, is with more than 40 years of international experience in hydrocarbon North Africa, including Libya, Egypt, Tunisia, and Algeria, also Middle East, South America, Brazil, Argentina, West Africa, and almost everywhere. Yeah, and at the end in Tunisia. Okay.
That's my colleague.
Okay.
I stand here, right? Okay. So, thank you very much. So I'm Jan-Pieter van Dijk, and substituting Stefano Santoni in all senses. Now, sorry, I have a cold, so. Now, this presentation is a complementary presentation on the one we did this morning as Dragon Oil and ETAP on the play concept of the Miocene in the Gulf of Hammamet. So for who of you saw this presentation this morning, it's quite boring because some of the slides are exactly the same, and it will just be the same story told by another person. But there are some other things in this presentation that focus on one of these aspects. So let's just go into the introduction for who didn't see the presentation this morning, where we are. Okay, this is the Bargoo license of Dragon Oil. Dragon Oil is a company that works in 6 or 7 countries, in the Middle East, North Africa, and this is one of our offshore exploration licenses. We have producing licenses, we have things in Iraq, limestone production, in Turkmenistan, in Algeria, in Egypt, Afghanistan, and this is our, let's say, license in Tunisia, where we already have drilled a well and we took over the operatorship from Cooper Energy some time ago. It's a very big, let me see how this works. This is the pointer, right? So it's a very big license, of course, offshore all along the Gulf of Hammamet. We identified this prospect Huta, that was explained by my colleague this morning, which has, according to us, a number of characteristics which are a little bit different from the ones that have been drilled and explored up to now. Here are some estimates on these slides of what we think how much could be the reserves in place, and we are quite optimistic. We like this, and let's talk a little bit about this prospect and why has it these different characteristics. Now, if you look at the petroleum system, this is nothing else than well-known knowledge. We need the source rock, reservoir rock, seal, and we need a few processes like maturation, migration, and trapping. Oil companies, they use these 6 components of the petroleum system to risk the money they put into their enterprises. So we do this also. You can see this in different papers in a different way, because of course for maturation you need also some rocks, and for trapping and for have a good seal you need some processes. It depends a little bit on how you classify these aspects. We like to do it like this, with some rocks and some processes. Now in green you see the ones that, let's say for the Gulf of Hammamet, are more or less ascertained. Nobody is too much worried about this. We see the source rock, the Fahdein formation. We know a lot about this, and everybody's quite comfortable. It's there, it has been maturing, etc. For the reservoir rock, we are looking at the Miocene sandstones, Umdewil group, Birsa, Zouaf, and we have some ideas that there is some new elements in here. That's why it's in red. And my colleague talked about this morning. We think they have, in certain areas, they are thicker because the deposition is not uniform. It's not everywhere the same. And the fields that have been discovered up to now, they always tackle the high structures in the Gulf of Hammamet, where we think the sections are, sedimentary series are more condensed. So the accommodation space in reality is outside these highs, but we have to get these sediments then, of course, in a trap. The seal, intraformational Miocene shales. We saw a lot of these shales, they are there, and you can seal and make stacked reservoirs, different layers with each different contact. So again, something that we know about, has been ascertained by other companies that have been producing, etc. In green. Process and maturation, Myopliocene age, more or less. We need some time, and we need to get the rocks into the oil and the gas window, and we talk about this. But basically, having been produced already from these, we know that there has been maturation. So this is something in the petroleum system that we are not too worried about. That's not too risky. Migration. How do we get this oil and gas into the sandstones? This is something that you can have different ideas about. Now this is in yellow because this talk of mine is extracting this specific element out of this story we tell to focus a little bit more about this. Trapping, in our case, being all the high structures in the Gulf of Hammamet already drilled and produced from, we believe that there can be other structures not yet drilled or discovered. And we have actually some of these that have been discovered already that we think they can be classified in this trapping mechanism, which is the inversion tectonics. Again, something that my colleague Hassan this morning talked about. So let's say that we had, our objective in this conference was to talk about what is red here. And I am left with the only one that is, is now in yellow. Okay? But in this talk, don't worry too much who didn't see something this morning. I will anyway tackle the other two red a little bit. So everything is based, let me see if I can point to, yeah. Everything is based on seismic interpretation and mapping of the Gulf of Hammamet, where we have a comprehensive database, 2D, 3D seismic, well stratigraphy logs. So we have a lot of data, and we built this model. Let's go on. Gulf of Hammamet is some old picture. It's not the best, but it is useful. Now, we saw also in the previous presentation, this is a little bit more extended to the south. It is a complex multi-stage tectonostratigraphic history. Sounds very nice and makes us comfortable that we have a lot of things to do geoscientifically, many things to discover. But let's try to simplify it a little bit. First of all, we have an episode of Mesozoic Eocene, more or less, so, where we have our source rocks and carbonates series deposited in an extension rifting area along the margin of the African plate. Excuse me, my dear Tunisian colleagues, that I simplify everything in this world so much, but I have to tell this story also to people that don't even know where Tunisia is. So I have to tell them a little bit more in a simplified way the things. Then we have a second episode, which starts more or less after the Eocene, to our opinion, and goes on until today, where we have a chain coming up from the north, which is moving and slowly incorporating what is now Tunisia into the deformation, and therefore we have an area where we are now that was an alpine foreland area with transtension and transpression. So we have a superposition of these structures on top of this nice African Mesozoic rifted margin. And that is where our sediments have been deposited, and this is the processes that have generated our traps. So we go from the source to the reservoir to the trap. Green, yellow, red. Nice. Almost a traffic light. In time, nice, very complex. I think this is something from ETAP people, this picture. Can somebody confirm this? It is still a mystery for us. So let's put these colors also on this. We have a first episode, Mesozoic, Eocene, etc. And we have the other two here. We're all G&G people, I think, here, so I don't need to explain too much about this. Here are the source rock, the Fahdain. And here are our reservoirs, here and there and there. Now what we did, to simplify the story, we did 1, 2, 3. 1 is the Oligomyocene, 2 is the Myopliocene, and 3 is the Pliopleistocene. You see, in each of them there are 2 chronostratigraphic periods incorporated, separated by our main unconformities. Good, that's nice and simplified. The source goes into the reservoir. That's the arrow. But how? Now, this is a composite seismic section, 2D and 3D data connected. One of our colleagues who is not here, he has a lot of experience in seismic mapping, and he nicely put everything together. We see it in the index map. No, wait a second. Here. It goes from one producing field, Marmura, through our prospect into the trough, then up to another one, the Baraka field. Here, down to there. Now, what is important in this section? Well, you can see it already. It's deliberately indicated in red, captures the eye. It is, of course, this and this. Because we can see the Mesozoic series here, cut by faults, and a little bit left here, with the source rock, the Fahdain, which is actually drilled in some places in these highs. So we can correlate this. We know where it is. And we have the seal of the Abiot and some Oligomyocene unconformities, and then the Langian, the pink, the turquoise one. And then we have one big sedimentary series and another one. So, and I think something should come up when I do like this. Yes. So here we have again yellow, in green in the base first episode. We have the alpine foreland areas where we have all these thick sediments localized. In this case, in the Jiriba Trough. And we have, let me see if I click, our alpine chain coming up by inverting part of this. So it's not a chain, it is a deformed foreland. Huh? It suffered from something that happened in the north of Tunisia, terrible tectonic shortenings in the Miocene, Pliocene, Pleistocene, maybe already still today. Let me see. To our opinion, let me see what comes up now. Yes, one, we have Oligomyocene foreland series for tuna on Eocene unconformity. Then we have a Langian unconformity, angular, cutting away many things. Two, that's our friend, the Myo-Pliocene foreland series of the de Wiel group, deposited on the Langian unconformity. And you can see many thickness variations from here to here, you see, in the trough, and there again, here and here. And then number 3, on the Messinian, let's simplify Messinian unconformity. I should be the first to tell you that there is, of course, a lot going on from mid-Messinian up to mid-Pliocene, up till we have another, up till we have this Plio-Pleistocene foreland series that have also suffered the inversions. So this structure is mid-Pleistocene. And we can see actually in many of the fields producing from the Gulf of Hammamet that they are inverted in the Pleistocene. Shouldn't worry us too much that a structure which contains hydrocarbons from which we can produce has been deformed so recently. Apparently it's okay. And probably also this is quite young. So now the question that we have is how this system then evolve in time? How do we get these hydrocarbons from the Fahdein in the Birsa, for example? Okay, we have this map, of course, a little bit about the very quick flash. Where are the source rocks deposited? Okay, on the northern margin of the extension of the African platform. We have, in the Eocene, we also have Budabus, of course, everybody knows him. But what happens in the Eocene? Unconformity, most of this Eocene is eroded. So we have no Budabus in some areas available to source our reservoirs. Here we go, it's away. Then, again, the Langian unconformity cuts. Most of the deposited have been deposited on the top of the Eocene, which is for tuna, etc. But cuts also a little bit into the Albian Cenomanian. And that's what we need. And we saw it in the section, and erodes this. So what we immediately see that we have a subcrop of Fahdein below the Langian unconformity. And as we saw in the previous paper, what is on this Langian unconformity? We have all these nice bioclastic limestones sitting there as first sediment. Okay, here we have some of these source rocks in the field. That's how they look like. Let's not stop here. Now, let's go and reconstruct it. This is some games we can play in the workstation by flattening the seismic. So let's flatten it on the Langian. How does it look like in the Langian? In the Langian, we have basically a landscape of outcropping Eocene and Mesozoic below the unconformity, you see? Here we have some Eocene sitting there. Here this is the Mesozoic and the Fahdein, and it comes and touches, and here we have other meso in these highs. So the Langian is it's terrible time to live, because there was a lot of tectonics and things going on, and angular unconformities in this area. What is this? This is, of course, the foreland bulging, as we interpret it now, from something that was a chain in the somewhere there. No surprise, but important for us because it generates a source rock subcrop. Now, next one is on somewhere in the Messinian. How does it look like? We already deposited, oh, let's go back. We already deposited the Miocene foreland sediments with all these thickness variations. Jiriba trough, very thick, Birsa Swaf, and on the high, thin sections. And some of us already also eroded during the Miocene. Yes, this looks a little bit like the picture of the previous speaker, because we have this Miocene chain here. What is inside this chain? Well, can be Miocene, can be Oligocene, can be Eocene. We can erode it and put the sediments here. So we have a source. But we have to look at what happens with our Vardeen's source rock. It's getting into the oil window. Okay? Maybe it was before, but... So when the Birsa in the Swaf was sedimented, the Vardeen was in the source. It was in the oil window already. And if we look at it now, last step, of course we have these other sediments, Pleistocene sediments on the top again. So it's pushing down, and the Vardeen is in the gas window. Yeah, in the gas window. So what was the issue? Vardeen is in the gas window, here it's in the oil window, and we have abiot production below a Al-Haria seal. So we cannot go from Vardeen vertically through this seal to source the Miocene, because it is a seal and stops the hydrocarbons from migrating. So how do we get this Vardeen in the hydrocarbons in the Birsa and the Swaf? In a period that is similar to what we are looking now. Because we have these traps, Swaf and Birsa, they have been generated only late. 1 million years ago, 1.5, 500,000, 700,000, pick it. So we must migrate this late. We must migrate this in a system as it looks now, more or less. Although they have been maturing from oil to gas after the deposition of these, during and after the deposition of this Miocene. You get it? So what is the... Look, here the Vardeen is subcropping below the unconformity caused by the movements in the Langian. So the Vardeen can go through this window and enter the Miocene. Like this. It can go vertically in the abiot, good, and then goes up. And trapped below the Al-Haria seal. But it can go in the Jiriba trough and migrate upwards to fill this, source this. That is what we are proposing. But if you look at the system, is it actually compatible with the presence of the hydrocarbons in various fields in the Gulf of Hammamet? So we check this. Let's just take a look around where we have our prospects by these inverted sandstone thicker than this one, but still in anticlines. We have the subcrop indicated here from the seismic mapping. And actually we have in the Jilibak trough always this subcrop sourcing anything that is around, the Baraka. Here we have other places where this subcrop appears. Okay? And we did this for the whole area where we have seismic data. And actually, we managed to explain some of the dry structures, which simply through this mechanism don't have access to hydrocarbons. Which explains sometimes that some of these highs that have been drilled, they were not successful. They were not filled with hydrocarbons. Why not? Because there was not a nice window of Vardeen peeping through the Langian unconformity to our view. Okay. Here we have some arrows coming up. We actually find hydrocarbons in these structures coming from this source peeping out. And can we actually predict also some of these structures that don't have hydrocarbons? We must do this, because this is a risk exercise. If this model actually shows that we can easily go into these structures, then we are comfortable, okay? That we can actually go into them. And other structures become more risky, and even some structures that were dry can be shown why. Because from this kind of window peeping through, you cannot arrive at something like this or other things. So that's fine, that works. Here's more regional. This connects nicely with the picture I saw in the previous presentation, also all the fields in the Miocene. And here we have all these windows and show where, from which window in the Vardeen, along the Langian unconformity could have been sourced. This fits. So we are quite confident that this migration model works. So, this is it. Very basic, very simple. We have a new play concept in reservoirs of the Gulf of Hammamet. It's a positive message I want to bring here, okay? We are a company that is looking for opportunities. We want to drill. We want to be confident that what we drill is actually a good prospect. We want to work in an area where you can still find new hydrocarbons, not where everything is already found. That's why we say it's a new play in an old basin. Old basin because the basin is already explored and produced from, and what we say creamed. If we take the play concept, the highs, it's what we say creamed. There is a flat understand which layers are maybe less accessible than others, because the type of migration predicts also, tells you a little bit how you distribute your risking on the different layers that we calculate prospective resources. Thank you very much.
But it seems from your section that the part near the path of
the part of the source rock that we think that can be addressed still. So there must have been a process where oil migration and later gas migration was going on. So I fully agree. Of course, we predict most of the things. We say, okay, most of the early migration and the trapping, most of these fields are all in the oil. But there is gas also already discovered. We have to take account of the fact that some of these prospects can be just gas. We have to take this into account. In fact, we did oil and gas cases. I don't know, Hassan, don't think you went into this detail this morning, but in our system of how we, let's say, how we calculate our expectations for these reservoirs, we have 5 levels: Birsa 1, 2, Zouaf 1, 2, 3. And so we make oil and gas cases for them and mix them in a, let's say, sort of probabilistic system. I agree. Let's say most of it we put in the oil, but we have gas cases. Yes.
That is exactly the meaning of my
Absolutely.
question. There is maybe some assessment for the model to be done.
Yes. Let's say if we only find gas, we cannot be too much surprised. It is one of the scenarios. But we expect oil and so.
Between so donc Langen and Grab carbonates and this reverse fault close to the traps, because your trap is faulted trap, okay? And if we have the migration from the Fahdan and following this carrier bed, okay? The Ain Rab is really a carrier bed. We have perhaps the shale above Ain Rab, but let's continue with immigration along this carrier bed. Yeah. How we will stop the migration till the Ma'mura field in your scheme, I mean. So you will have double sourcing, Ma'mura and vertically your new prospect, the Hout. Huh? If I understood well your conception about the migration.
Yeah.
Laterally and vertically.
Yeah, okay. So I understand your question. Yeah. It looks from what we know that this, on top of this Lange nonconformity, we have this Eingrab bioclassic limestone. So let's say that this would be the carrier bed, first carrier bed. So, in fact, most of the wells, they have there's oil in the Eingrab. Yeah? It's well known, so it's okay. It's not new for the whirling system on the Langian nonconformity. Okay, top lap, down lap, anything can happen. So we can easily go from, if we have a down lap from the Langian nonconformity albiot into one of the Birsa and Swaf sands, anyone. Okay? So we have to imagine a complex sedimentary system of Miocene sandstones and shales which show some interconnectivity, not only along the faults, because we believe that the faults probably are more a sealing element. So they are more a risk. If we have thicker sands, not big offsets, go through it, like Birsa. You see, but if they offset too much, it constitutes a risk, more than a migration facilitator. So we rely on sedimentary complexities, like channels of thickening, interconnectivity between the sands. So that's why I'm so interested to see what is laterally happening. Because they interconnect, you get the hydrocarbons in one or the other with ENI.
Some dialogue.
I'm sure my colleague Hassan already showed that this is a asset attached to the Marmura license.
Case,
so
you don't have any issue.
No, we have no issue. We are more. Each one is hoping in success of the other, of course, because we create. Anybody who has success before the other helps the other one. So we are we are opposite. We are not competing here. We are hoping.
Okay.
This is what we call a one-go well. This must confirm this concept as well. It's very expensive, 15 million, 20 million, whatever. Doesn't matter. It's the point. We are doing the well site survey now. So the boat is waiting to depart. Maybe, I think, should have been ready or starting now. I think the colleague is occupied with this, is walking around and doing some presentation in the afternoon about other things, geophysical operations. But we are doing this well next year. And then we will know. I mean, maybe next year this well will tell that everything I have told today was nothing, was not true, was nothing. You cannot rely on this story. It's not the point. We generate concepts to risk and invest. Then we drill. If we have success, it means that the Gulf of Hammamet opens potential. Because this concept could be in many places. But we need a lot of 3D seismic, we need to, so it means this is what happens in a new play in an old base. A new play generates, even if we find just little hydrocarbons in a few layers, it is a concept that then appears to work. Okay? And then with ENI, yes, we give them hydrocarbons because they have the facilities, and that's what you do normally. This makes our enterprise less expensive, less risky, because if we have the hydrocarbons, we can find some agreement with other companies to share the facilities. It's good. It's all part of the...
Hope this scenario or this concept work, because if the scenario work, will be upgrade this play over.
Out of the box, right, that's an example.
Thank you very much for this
Thank
nice
you, sir.
discussion, and sorry for this delay. Thank you.
Thank you, thank you all.
Okay.
Have a nice lunch.
Sees a call for census. The boss wanna know what's going on. So Joseph and Mary hit the road, with Mary nigh on 9 months gone. And you know we're talking about a hell of a walk. Had no place to stay. They tried the inns and the hotels. The message was plain as day. You get no refuge, no respite, and no sanctuary here. No refuge, no respite, and no sanctuary here. Well, now you get no refuge, no respite, and no sanctuary here. No refuge, no brother, but they run by the Bowling Green. Now there's a lot of folks are looking over the edge of that plate we've piled so high. When they all decide to come over the border, time to kiss it all goodbye. There'll be no refuge, no respite, and no sanctuary here. No refuge, and no respite, and no sanctuary here. No refuge, no respite, and no sanctuary here. No refuge, no respite, and no sanctuary.